Hello, we are Team Skywalker, and for our final project, we analyzed components from UCI's SAE electrical car project, Joule.
The first component of the powertrain system are the two air-cooled DC motors. Each motor has a peak torque rating of 98 Nm running at a maximum of 500 amps. Through simple heat transfer calculations, we found that the motors were producing 1.6 kilowatts of heat loss. By running a thermal loading simulation, we found that the motors reach a maximum temperature of 164 degrees Fahrenheit, well under the rated maximum operating temperature of 250 degrees Fahrenheit. This is partly due to the internal fan producing forced convection on the copper windings. We ran a second simulation without the internal fan and found that the windings can get as hot as 490 degrees Fahrenheit.
For the second simulation, we ran a static analysis on the chain link of the powertrain system. The scenario considered was a chain in tension due to typical performance use. To simulate this scenario, the chain was assigned material properties of normalized 4340 steel. A fixed geometry restraint was placed on the left joint of the chain link, and a load of 500 pound force was placed going rightward on the symmetrical cross-sectional wall of the chain link. The load was placed in this orientation in order to simulate a tensional force. In the first iteration of the chain, we used aluminum as a material, however, we found this caused it to fail at low loadings. From the stress plot, it can be seen that the max stress of the 4340 steel chain is 400 megapascals. This is less than the yield stress of 710 megapascals. Therefore, the part will not yield due to typical performance use.
A static analysis was conducted on the differential carriers, which are mounted on the chassis. The left and right carriers are fixed on the chassis with a 1,000-pound remote load applied where the sprocket of the differential is located. The left carrier had the highest stress, almost yielding. The second iteration contained a cross brace which distributes the load between the right and left carriers. This cross brace reduced the minimum factor of safety to 6. A beam analysis was conducted on the chassis to simulate the effects of the maximum torque produced by the motors. Here are the boundary conditions and the remote torque applied on the chassis where the motors are mounted. The first iteration yielded so the two front tubes were triangulated to distribute the stress between the top and bottom tubes. The maximum stress was decreased significantly, which is shown here in this graph.
A fluid static and buckling analysis was done on the rear wing assembly to ensure no yielding or significant displacement occurs with the downforce and drag generated at 40 miles per hour. The analysis for the rear wing mounting hardware began with a fluid flow analysis conducted in ANSYS Fluent to find the lift and drag forces of the rear wing. With the load solved for, we could apply the boundary conditions to represent a bearing load of 24.3 pounds on the top portion of the bar mount. We could hold the bottom portion of the top of the bar mount with split line fixtures to represent a washer and a bolt as well. The plate mount is held fixed at the bottom portion, represented with the green circles. It is also exposed to a bearing load of 42.4 pounds on the top portion to also represent a bolt. The original component of 1/2 inch in outside diameter experiences a von Mises stress of 60.8 thousand psi. Unfortunately, it yields. It also experiences a displacement of 1.29 inches. To fix the yield, we adjusted the outside diameter to 3/4 of an inch. This brought down the von Mises stress to 32.3 thousand psi. It also mitigated the displacement to 0.373 inches. The original iteration of the mounting hardware does not yield under the prescribed loads. However, running a buckling analysis reveals that 11.2% is needed for the structure to buckle. By doubling the thickness and using proper triangulation on the structure for iteration 3, we were able to improve the buckling factor of safety to 3.38.
This concludes our video. Thank you.